Chapter 15 is equilibrium, and equilibrium provides the basis for the acid-base chemistry and the solubility chemistry we have to cover in chapters 16 and 17. You learned the chemical equations in Chemistry 1210. You have to bring them back. The equilibrium concept, it is really simple. Products over reactants. The application requires the use of very specific methods. Learn them and you will be fine. So whenever we start a chapter, I always make a little laundry list, and here it is sitting as usual. And for this chapter, you do need to work these sample exercises. Maybe you got away without doing things in 1210. This is not the time. In 1220, you have to do it. I can only give you an outline of the concepts. What really hit me with online teaching last semester is I can say things, but then we all have to use them. And it's not until you use them that we can have a really good discussion. So you need to be able to apply a lot more than you did in Chemistry 1210. Some of the problems are very straightforward. All of them, they're just going to have to write an equilibrium expression. Products over reactants, that is not hard. But others are going to require thinking, and that's going to take mastering these concepts and then applying them. All right, forewarned is forearmed. So what is equilibrium? You've looked at reactions and you've seen it's done. Well, it really isn't done. Just like we had solution chemistry, where a solid is in equilibrium with the ions in solution, same thing with equilibrium. The textbook example they give is dinitrogen tetraoxide, which is colorless, can go to form 2 molecules of nitrogen dioxide, which are brown. Now, this actually is smog. If you've ever been in a place where there is smog, this is really what you're looking at, nitrogen dioxide. So what I need to teach you here is, what is K? K is the rate constant forward divided by the rate constant reverse. And you can see there's a coefficient here, which is going to match the coefficient in the balanced chemical equation. So again, I know we've just been through kinetics where you did not do this, but in equilibrium you do. What we're also going to do is take a look at concentrations over time. This example has this as the reactant. It has this as the product, and you can see the reactant goes down over time, the product builds over time, but there gets to be a point where we don't change concentration. That is called a steady state, and that is where equilibrium is actually achieved. We can look back at chapter 14 and take a look at the kinetics. For the disappearance of N2O4, there is going to be a point where the rates level out. For the appearance of NO2, there's going to be a point where the rates level out, and equilibrium is achieved when rates are equal. This is very conceptual. You probably have to think about it a little bit. Please do. It makes all the difference. Take a look at these two pictures. This is the essence of equilibrium. Please come to the lecture Zoom where I have more time to talk. World. So here again we show the same equation and we say, hey, here it is frozen. It's colorless. That means we primarily have the dimer, dinitrogen tetraoxide. As we warm up, we start to see the appearance of brown color, and when we get to room temperature, we see a dark brown. That does not mean there is not any dinitrogen tetraoxide. What has been achieved is equilibrium, and that is designated by these double arrows. Couple of slides. So, I kind of said a little bit, but now I'm going to say the real facts. Many reactions appear to stop. This was our Chemistry 1210 prime arrow, but they are actually reversible. When you see the arrows going in both directions, that means reactant can form product, product can form reaction. And we need to say that at equilibrium, the concentration of all the reactants and all the products in a closed system will not change. That's where they level out on the graphs on the preceding slide. And it is dynamic. Again, it does not stop. The opposing reactions proceed at equal rates. Take a look at those graphs again, because that's a graphical illustration. So what do I want to say? To make this really simple. A is a reactant and B is a product. The forward reaction is A going to B. And in chapter 14, you learned how to write a rate law. And you would say KF is the forward reaction. But now we know there can always also be a reverse reaction where B, the product, can go back to form A, and it also has a rate equation. If I set the two of them equal, if I equal the rate forward equals the rate reverse, that's where I will have KF times A is KR times B. So the person who developed equilibrium said, let's rearrange this equation. Let's put the rate constants on the left. Let's put the concentrations on the right. And this is how the equilibrium constant is defined. It is symbolized by the letter K. You will see a KP, a KC, a KA, a KB, a KSP, and a KF. All of them are the same thing. They are products divided by reactants. That's when I said it was a simple concept. It's not as difficult. Working problems may be hard, but the concept itself is easy. It tells you the extent, and we'll get more about that in the later sections of this chapter, but it tells you nothing about the speed. Equilibrium is totally divorced from the speed. Step back, okay? So, in the last chapter, we learned about mechanisms, and I wrote this all down ahead of time. I learned teaching online. It's not like teaching in person, so I had to write everything down. What if I have a different sort of equation where I form a product and it proceeds by two different steps? Here is step one. Here is step two. We learned in the last chapter that when you add the mechanism together, you must come up with the given equation. And what I did here, to prepare ahead of time, is to write down all the different expressions and equilibrate them. So if we're looking at K1, which would be referring to step one, we could write this equation. If we're referring to K2, we would be referring to step two. Remember in the last chapter that when you add the equations, what you do is you multiply the multiply the equilibrium constants. So essentially, that's what I did here in the bottom line. Will you be expected to do this in an exam? Heavens no, it takes like way too long. But essentially, this is the message we're trying to send home. Remember, in chapter 15, a mechanism may be proposed, but you do not know it is definitive. My PhD thesis was mechanistic studies. I could do all the measurements I wanted, but it was the best evidence I had at the time. So know that the equilibrium constant is an equilibrium. What it is the products divided by the reactants, and I'll even